Hi, Mark. All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. Welcome to the second class session for EGME 47. Today we're actually going to start the real content for the class. And so how's everyone doing today?
Good. How about yourself?
All right.
Good.
How about you?
Good. Yeah, I'm good. Thanks for asking. All right, and so today we're going to start our lectures on conductive heat transfer. Okay, so remember last time we talked about how there's three main modes of heat transfer. There's conduction, convection, and radiation. So today we're going to start with the simplest one, which is conduction. And so we're going to introduce the idea of what conduction is, what affects it, and we're going to solve some elementary problems. Right? Okay. So before we begin, are there any questions I can answer? All right, okay, so let's go ahead and get rolling. All right, so the topic for today, and we'll probably finish it up on Monday, is conduction heat transfer in Cartesian systems. Oops. Okay, and Cartesian systems, all I mean is that the our domains are going to be rectangular. Okay, so they follow like the basic XY coordinate system, or in our case, it's just going to be one dimensional, so it's just going to be X. So starting next week, at the end of next week, we're going to look at polar systems, and so that's going to be cylindrical coordinates and spherical. But first, we're just going to start with Cartesian because that's kind of the simplest thing to do. Okay. All right. So first, let's recall the definition from conduction. Okay. Okay. And so if you remember from Monday, conduction is the transfer of heat or the transfer of energy in a medium due to molecule to molecule contact. Okay. Right. So remember we showed that image on Monday where we have a medium where all the molecules are kind of bouncing around, and when you have a temperature difference from one end to the other one, the molecules transfer energy from one to the other. Okay. And remember, the difference between conduction and convection is that our medium here is stationary, right? So that means it's not moving. And so when we have conduction, the primary formula that describes it is known as Fourier's law. Okay. And so Fourier's law is stated as follows. And so we have Q, where Q here is the heat transfer rate, is equal to minus K times A times the derivative of temperature with respect to space. Okay. Okay. So this is the main formula that determines what heat transfer is. Okay. In conduction anyway, and we're going to define what each of these terms mean. Okay. All right. So let's start with Q. Okay. And so Q here refers to the heat transfer rate. Okay. The key words here being rate. Okay. And so this basically tells us how quickly energy is being transported through this medium. Okay. And the units for this, the units for heat transfer rate are given as watts. Okay. Where if you remember from thermodynamics, watts is the unit of power, and it's basically defined as joules per second. Okay. Okay. All right, K. So K here is a very important quantity, and probably you haven't seen it before in your previous classes, okay? Because it's something that's pretty unique to heat transfer, and this is what's known as the thermal conductivity of the material. Okay. And so we'll talk about thermal conductivity more in a bit, but basically the thermal conductivity is a measure of how well the material can transport heat, okay? And so certain materials do a much better job at transporting heat than other ones, right? And so for an example, metal can transport heat very, very easily, okay? Whereas something like a ceramic or something like, or glass is not so great at transferring heat, right? If you've ever wondered, why coffee mugs are often made of ceramic, that's mostly just so that you don't burn your hand when you pick up your hot cup of coffee, right? Whereas if you have like an aluminum coffee cup, you're probably going to burn your hand most of the time unless you're wearing gloves. Okay. All right, question. So the units for this be watts per meter K? Yes, actually, yeah. So the units for thermal conductivity is watts per meter K, where K there stands for Kelvin. Correct. So that's the units for thermal conductivity. Or another way to express these units, because K, using Kelvin as a unit for K sometimes gets confusing. Sometimes we use degrees Celsius instead of Kelvin. And so sometimes you'll see this as well. And personally, I like that one a little bit better, because then I think people know of degrees Celsius more often than Kelvin, for thermal conductivity. Yeah. Mm-hmm. Yeah, very good. All right, A. So A here is nothing more than just cross-sectional area. Okay. And so basically this is saying that, if you have a bigger cross-sectional area, then more heat's going to get transferred. Okay. And area is pretty simple. The SI units for area is just going to be meter square or centimeter square. Okay. Okay. All right. And then I'll talk about the derivative in a second, but let's talk about what the T stands for first. Okay. So the big T here stands for temperature. Okay. And temperature, typically for this class, a lot of times we're going to use degrees Celsius, but sometimes we might use Kelvin as well. And then the English units for temperature would be like degrees Fahrenheit. Okay. But most commonly in this class, you'll see me use degrees Celsius. Okay. Right. And so that's what all the symbols mean. And then before I kind of put all this together in terms of the equation, I do want to talk about what that derivative means, but I've kind of run out of space here on this page. So before I turn the page, are there any questions on this? Okay. All right. So let's talk about the derivative, right? Because the temperature doesn't appear in our equation just by itself. It appears as this derivative term. And so let's talk about what that means. Okay. Okay. So our derivative term here is dt dx. Okay. And this is known as the temperature gradient. Okay. Have you guys heard the term gradient before in a previous class, or maybe you've heard it in terms of paint or in terms of
like
of design? Wait, say again?
Like pressure gradient of fluids?
Yeah, exactly. Perfect. Yeah. So gradient is Oh yeah, yeah. And so gradient basically just means that you have a change in something over space, right? And so temperature. Oh, in calc, perfect. And so temperature gradient just basically means we have a change in temperature over a given space. Okay. Okay. Because remember what we talked about on Monday, what the number one rule of heat transfer is. The number one rule of heat transfer is that heat goes from hot stuff to cold stuff, right? And so if you have a hot temperature and a cold temperature, that naturally means that you have a temperature gradient, right? And so this term right here basically tells us that, in order for heat transfer to occur, we have to have a temperature gradient, right? There needs to be a hot end and there needs to be a cold end, and then the heat's going to go from the hot to the cold end, okay? It is physically impossible for two objects of the same temperature to exchange any heat, because if they're the same temperature, then their temperature gradient is going to be 0, right? And so if you have an object that's at 25 degrees C and another object that's 25 degrees C, these two are not going to exchange heat at all, or no heat transfer is going to occur, okay? And so it's a very simple example. Let's consider a case where we have a cylinder, okay? Okay, so I'm going to draw a cylinder just like this. Right. On the one hand, on one side, we're going to have a temperature T1. Okay. Question: so they seek equilibrium? Absolutely, yes. Yeah. So the main reason heat transfer occurs is so that the objects can reach equilibrium. That's correct. Yeah. And so every object wants to seek out that equilibrium with each other, where everything is going to be the same temperature. And so whenever you have a temperature difference, then they're going to exchange energy, or they're going to exchange heat in order for them to reach equilibrium. Yeah, that's a great observation. All right, and so on one side, let's say we have a temperature T1, and let's say that this is let's say it's 100 degrees Celsius. Okay. And let's say on the right side, we have a temperature T2, where this is, let's say 50 degrees Celsius. Okay. Okay. And so in other words, we have a situation where T1 is greater than T2, right? And so we have a temperature gradient, right? And so what this tells us is that heat is going to go from left to right. Okay. So we can draw an arrow there for Q that goes from left to right. Okay. All right. And so that's the basics of Fourier's law. And so Fourier's law basically says that whenever you have a temperature gradient, you're going to have some heat transfer that occurs that's proportional. That's proportional to the difference in temperature. Okay. And then it's also dependent on the other factors as well. All right. So let's go back to the equation and let's talk about what those other factors are. Okay. Actually, I'm gonna do that on the next page. So before I go there, are there any questions on this? Okay. All right. So let me go ahead and write Fourier's law again. Okay. So we have Q is equal to K times A dt dx. Okay.
Professor, isn't it negative K?
It is negative K. Thank you. Yes. Did I miss that? Yes, I did. Okay. Okay, and so let's go through each of these terms in this equation again, and let's talk about how they affect the heat transfer. Okay. All right. So let's start simple. So let's start with the cross-sectional area A. Okay. Right. And so the position of this variable here tells us that the larger the cross-sectional area, the more heat is going to be transferred. Okay. And so we have two situations. And so let's say that we have a situation like this, right? So let's say we have a thin cylinder, okay, versus a very wide cylinder, right? And the temperature difference is the same on both sides. Okay. Right. And so T1 and T2 are the same. And so, we can fill in the same values that we had on the previous page, right? This tells us that, because the right side has a greater area, that means that we're going to have a higher amount of heat transfer in this situation. Okay. Okay. The temperature difference is exactly the same. The only difference here is that, we have a wider area. Okay. And so one way that you can think about this is, think about it like freeway traffic, right? And so if you have more lanes on the freeway, right? So let's say that you're you're on the 57 right outside Cal State Fullerton. It's a very nice, 5-lane wide freeway. Generally speaking, the traffic flows pretty quickly. But if you try to imagine that same situation where you try to have the same amount of cars that gets to the freeway, but you only reduce it to a 2-lane freeway, things are going to go a lot slower because the cross-sectional area or the number of lanes there is small, right? And so the more area that you have, the more heat transfer that you're going to that's going to take place. Okay. All right. I want to hold off talking about the thermal conductivity for a second, but let me talk about the temperature gradient again. Okay. All right, so the temperature gradient kind of has two components to it. And so there's dT on top and dx on the bottom, right? And so basically this expresses a change in temperature over a distance. Okay. Okay. And there's kind of two ways that we can increase or decrease this value, right? And so there's the dT part, right? And so the dT part here represents a change in temperature, right? And so if we have a greater change in temperature, that means we have a greater amount of heat transfer. Okay. Okay. And so, if we look back to our previous example, if we said T1 instead of being 100 degrees Celsius, maybe that's 500 degrees Celsius instead. And so we have a difference of 500 minus 50. That's going to create a much bigger amount of heat transfer. Okay. But the other part of this that I think people don't really think about a lot is the dx, right? where dx here represents kind of the distance, in between the temperature differences, okay? And so notice that dx here is in the denominator, right? And so what this tells us is that the shorter the distance, the higher amount of heat transfer that has to occur. Okay. And so, if we looked at these two situations, right? If we looked at a situation where we have T1 and T2 and they're only separated by a very short distance, right? And so the temperature difference is fixed, right? If we shorten that distance to such a small amount, then the amount of heat that gets transferred has to increase in order to compensate for that smaller distance. Okay. All right, so I'll go ahead and illustrate that on the next page with kind of an analogy. But before we do that, are there any questions on this?
Dr. Chen,
Yeah.
what does the negative indicate?
Yeah, so that's a great question. So the negative indicates that is just to make sure that we have positive heat transfer, in the direction from hot to cold, right? So actually, let me go ahead and illustrate that on the next page. But this negative here is just basically to correct for the signs, because normally if you have a heat transfer or a temperature difference in a certain direction, then this derivative term here is going to be negative. And so that extra negative out there is just to kind of cancel that out, just to make sure that we have a positive heat transfer. Yeah. All right, question. So is this distance in all dimensions? So yeah, so that distance, it can be applied to in all dimensions, but right now we're just considering just one-dimensional heat transfer. All right, so actually let me go ahead and illustrate why that negative is there on the next page. And so if we look at our example again, and so let's say that we have 100 degrees C here, 50 degrees C here, okay? And then let's say that this x1 here, or the location for this left side, we'll say this is at 0 meters, and x2 here is at 1 meter, okay? And so this is T2, T1, okay? All right. And so normally, we expect the heat transfer or the heat transfer rate or the heat to go from left to right, right? And so we expect the heat to go in a positive direction. But if we actually compute the temperature gradient in here, right, and so we just use simple differences, right? And so here we can compute the temperature gradient as T2 minus T1, all divided by x2 minus x1, okay? If we plug in the numbers for that, we have 50 degrees C minus 100 degrees C, all divided by 1 meter minus 0 meter. And this gives us negative 50 degrees C per meter. Okay. And so in order for our Fourier's law to end up positive, then we need that extra negative out in front just to cancel out this negative here. Yeah. All right. And so going off that same example, let's say that we have a similar situation where we have kind of a smaller pipe here, okay? Where this distance right here, let's say it's maybe only 0.25 meters, okay? Right, and so because the distance that the heat is traveling here is shorter, then the amount of heat transfer here has to be greater, right? Because let's compute the temperature gradient in the same way, right? All right, so if we compute dt dx here, we're gonna have 50 degrees C minus 100 degrees C all divided by 0.25 minus 0, okay? And these are meters, okay? And so we compute that, then we get a temperature gradient of negative 200 degrees C divided by meters. Okay. right? And so
Professor,
oh, go ahead.
sorry, does this assume that our area is constant?
Yes, it's assuming the area is constant, correct. Yeah. Yeah, and so in this case, with all the other properties held constant, and we're going to assume that the thermal conductivity is constant as well. You can see that when we make the distance, 1/4 of what it was, then we end up with 4 times as much, heat transfer, right? And the only thing that we changed was the distance in between them, right? And so I think that's an important thing to remember with that gradient. That is that it's, I think people think about that temperature gradient as purely just a difference in temperature. But the distance on which that difference in temperature occurs, makes a big difference as well. And both that distance and the temperature difference make an impact on the computation of the gradient. Okay. All right, any questions on this? All right, okay, so let's go ahead and talk about the thermal conductivity now. Okay. All right, so thermal conductivity, remember this was our property K, okay? And so to give this a formal definition, this is a property of the material which reflects how some materials are better at conducting heat than the other ones. Okay. And so, the thermal conductivity here is not really much different from things like the density or things like the Young's modulus or like the viscosity or, for fluids, right? And so it's simply just a material property. It's just one of the thermal material properties. Okay? And so typically the thermal conductivity for material is determined experimentally, right? And so what that means is that, scientists and engineers and technicians have basically taken, a bunch of materials and tested it in the laboratory about how well they can transport heat. Okay. And generally, you can look these up in a table online, right? And so if you have a certain kind of material, there's probably a lot of data sheets online that you can use to determine, what the thermal conductivity is, if it's not already given to you. I think someone earlier mentioned that, a lot of times when you purchase a material or when you purchase a certain product, then it'll tell you, what the thermal conductivity is. Okay. And so it's we're not going to go through and name different materials and list what the thermal conductivities are, because there's literally a bajillion different materials out there. But I do want you to remember some rules of thumb, because there are some trends that you can follow that'll tell you, what the thermal conductivity is within a ballpark. Okay. Okay. And even though these rules of thumb, they're pretty simple, but I think they give you a good sense of, how certain materials will behave in terms of their thermal behavior. Okay. All right. So number one, number one concerns the different phases of matters. And so generally speaking, the thermal conductivity of a solid is going to be greater than the thermal conductivity of a liquid, which is going to be greater than the thermal conductivity of a gas. Okay. Okay. And so a solid is going to be much better at transporting heat than a liquid, which is going to be much better than a gas, assuming all of these are stationary, right? Because remember, as soon as you have a moving fluid, and so if you have a moving liquid and a moving gas, then you have convection that you also have to take into account. But for strictly a stationary material, solids are going to be better than liquids, which is going to be better than gases. Okay. Right. And the reason for this kind of goes back to how conduction occurs in the first place, right? So remember, conduction occurs through molecular transport, right? And what do we know about the molecules in a solid versus the molecules in liquid versus the molecules in a gas, right? And so for a solid, those molecules are packed much more tightly together, okay, in a much more uniform fashion. Okay. And then liquids, even though liquids, the molecules are packed pretty closely together, they're not as tight as solids, right? But they are still pretty close. And so that's why you have liquids generally are better at conducting heat than gases. Where gases, there's a lot of empty space between gases. Okay. All right. And so that's the first rule of thumb. And so that's usually, a pretty one that'll get you pretty far. Another one that comes up quite a bit in engineering concerns metals versus non-metals. Okay. Okay. And so generally speaking, most metals are going to have a higher thermal conductivity than non-metals. Okay. And the reason for this, again, goes back to their molecular structure, right? And so what do we know about metals? And so metals, we know the molecules are organized in a very, very structured, uniform way. Okay. Okay. The analogy that I always like to think about when I think of metals, the molecular structure of metals, is that they're all kind of like little soldiers that that are perfectly disciplined and organized in neat rows and columns, right? And so because they're so uniform, the heat and by that same token, electricity can flow through that metal, very, very easily because the molecules are so close to each other and they're so uniform. Okay. Right. And if you compare that to the molecular structure of some non-metals, so things like a glass, things like ceramics, these are not as good at conducting heat. Okay. And the interesting thing about thermal conductivity is that it has a very, very wide range. And so, you might have some materials with extremely low thermal conductivities. Those would be like materials that are supposed to be insulating. So things like your oven mitt is going to have a very low thermal conductivity. But on the other end of the spectrum, you have some metals where heat travels through that almost instantaneously. So things like copper, basically all the metals that you used for electrical wiring, heat is going to go through that extremely easily as well. Okay. Any questions on this? Okay. All right. And so now that we understand Fourier's law and we understand the factors that go into it, let's talk about the equation that we're going to use a lot in this class called the heat equation. Okay. All right. And so Fourier's law is great. Fourier's law is one of the fundamental equations for heat transfer, and we'll use it, a lot in this class. But in terms of actually solving for something useful in terms of engineering, Fourier's law is not as helpful, because Fourier's law just gives you a measure of heat transfer, which is important. But if we're doing any kind of thermal engineering, a lot of the times what we're actually interested in is we want to compute what the temperature is in a given object. Okay. Okay. Because if you're doing the thermal design of some kind of device, so let's say you're doing the thermal design of an engine, maybe you're doing the thermal design of a satellite, right? What you're interested in is, is my engine going to melt itself? Is my electrical part going to melt itself? Is this going to be a safe temperature to operate on, right? And so if you're designing a device that is meant to be handled by humans, you want to make sure that it's a safe temperature for people to pick up and handle and not hurt themselves, right? And so even though Fourier's law gives us a great way to compute heat transfer, a lot of times what we're interested in is actually temperature, right? And if you look at the structure of Fourier's law, okay, a lot of times we have a little bit too many unknowns here and not enough equations to solve them, right? Because if you don't know what the temperature is, then you can't compute this. Or you can't plug in for this, right? And if you don't know what the temperature distribution is, you can't compute Q either, right? And so the way that this equation is structured makes it a little bit difficult to actually solve for temperature, right? And so for that reason, a lot of times we actually use a different formula to actually compute temperature, and that's what's known as the heat equation. Okay. All right. And so normally, this is the part of the class where we go through kind of a long derivation for what the heat equation, or how we get the heat equation. But I think it's I don't like to do derivations all that often. I think they have a place, in some places. But for such a fundamental equation like this, I think it's more important to kind of just state what it is and then talk about what each of the different terms mean and how they behave, right? Okay, and so the heat equation is given by this right here. Okay. If you are interested in the derivation, I think the book does a really great job of going through it. Okay. But in the interest of time and in the interest of doing an example, I'm not going to do that. Right, and so that equation right there, that is your heat equation. Okay, and so you can see here it's a partial differential equation, with lots of scary terms. But just like we did with Fourier's law, let's go ahead and break this up kind of term by term and see how each of them, see what each of them mean, and talk about how each of them behaves. Okay. All right, so let's go from left to right, and so let's start with the double derivative here. Okay. Okay, and so you can see from this term that this is a double partial derivative of temperature with respect to x. Okay, and here x kind of represents the same thing that as it did in Fourier's law. X here represents some kind of physical distance or physical space. Okay, and so what this term here describes, or what this term here governs, is how temperature is going to vary in space. Okay. And by space, I mean just, physical distance. So X, Y, Z direction. Okay. All right. And so, the form of this derivative is really important, because notice how it's a second derivative. Okay. And so most of the time, whenever you have a second derivative in, a second derivative in applied sciences like this, or in applied engineering, what that tells you is that this is some kind of diffusion term. Okay. Okay. So have you guys heard the term diffusion before? Veins. What do I mean? I'm not sure what you mean by veins. Oh, varies. I'm sorry. Yes, this is varies, not veins. Yeah. Yep, no problem. Yep. So have you guys heard of the term diffusion before in a previous class?
Definitely would have heard it in chemistry.
Okay. Yeah, that's a great place to hear it. Yu-Gi-Oh. Yeah, they might have mentioned that sometime in Yu-Gi-Oh as well. I'm pretty sure. Yeah. So diffusion is actually a pretty important term, and it's actually pretty simple than you think, right? And so what diffusion means is that diffusion, anytime you see diffusion, all it means is whatever quantity that you're looking at is going to spread out equally in all directions. Okay? And so by the temperature here being in the second derivative, this tells us that the temperature is going to spread out equally in all directions. Okay? Okay. And the other keyword there is passively, right? And so, kind of without any kind of active forcing, the temperature is going to naturally spread out. Okay. And so visually, it looks something like this, right? And I think the example that I like to give is, spraying an air freshener, right? And so everyone's kind of has like a can of like Lysol spray that they've seen before, right? And so, if you've ever taken one of those sprays and you kind of just sprayed it in the air above you, right? Maybe you have a cloud of Lysol spray that looks something like this at a certain point, okay? Right. And then eventually, that Lysol spray is going to spread out through to all the other corners of the room eventually, right? And so it's not going to happen right away, but eventually it's going to spread out, through the rest of the room. Okay. Okay. And so that action of spreading out passively that's diffusion. Okay. But if you can kind of imagine what's going on, you probably notice too that if you at first when you spray the Lysol, and you stick your head in the Lysol cloud, it smells really intense, right? It smells it smells like you're going to get lung cancer or something, right? I don't know if you guys I don't enjoy the smell of Lysol spray, but it's a good example, right? And so initially when you first spray it, you have this kind of very condensed concentrated cloud, it smells very strong. But as that cloud kind of spreads out to the rest of the room, that smell gets a lot less strong, right? And so the way that we talk about that is that the smell kind of diffuses out through the rest of the room, right? And so on the left here, when the cloud is still small, we have a small, intense cloud of smell. Okay. But after it spreads out, that smell becomes a lot less intense. Okay. Okay. right? And so that smell covers more area, but it's less intense, right? And so this example here kind of illustrates exactly how exactly how diffusion works, right? And so diffusion is kind of a passive spreading of a material, with an associated lowering of intensity. Okay. And so temperature works exactly the same way. And so what the heat equation is telling us is that, if you have kind of a concentrated, if you have a really high temperature at one place, through the action of heat transfer, then that temperature is going to diffuse out or spread out, in all different directions, equally. Okay. Right. And so that's the diffusion term, right? And so, the fact that the temperature here as a second derivative tells us that it's a diffusion term, and it tells us that, this is how we can expect temperature, or this is how we can expect energy to behave. Okay. Any questions on this? Okay. All right. And so that's the diffusion term. So now let's talk about this term. Right. And so we have this Q dot over K, right? And so this Q dot over K, this is known as the thermal production term. Okay. And what this term accounts for is for any cases where we can produce thermal energy within our system. Okay. Okay. Right. And so I know what probably a lot of you are thinking. You're probably thinking like, hey, wait a minute, creation, destruction, right? Like we can't create energy. That's illegal. That's against the rules, right? And you're right, right? And so in the absolute sense, energy is completely conserved. And so we can't create or destroy any energy. But, one thing that we can do with energy is that energy can change forms in between different ones, right? And so remember, there's lots of different kinds of forms of energy that there are in the world, right? So thermal energy is one form of energy, but we also have kinetic energy, and we also have, potential energy. We have chemical energy. There's lots of different forms of energy. And so even though, energy by itself in its raw form can't be created, it can be transformed from one system to another, right? And so in this class in heat transfer, most of the time we're only really concerned with just thermal energy. Okay. And so since we're just considering just one form of energy, it is possible to create thermal energy by converting it from a different form. Okay. Okay. And so we can do, you can actually do an example of this, right now, right? And so take your hands, assuming they aren't really sweaty like mine, right? And so if your hands are relatively dry and you just rub them together, right? If you rub your hands together, what do you feel? Like you feel like your hands are starting to get warm. And so the reason for that is, as you rub your hands together, the kinetic energy that your hands are developing by being rubbed gets converted to thermal energy through the action of friction, right? And so in that sense, when you rub your hands together, we have some thermal production because you're creating thermal energy from kinetic energy, right? You feel evil. Yeah, that's what evil villains like to do, like to rub their hands together. Yeah. And so I think people get confused with this term because they think, thermal production, that doesn't make sense. We can't produce energy, but you can convert it from one form to another. Okay. All right. Actually, let me choose a different color. We choose red. Okay. All right. And the last term of the heat equation here is this one, which is our unsteady term. Okay. And so it's the term with the time derivative. Okay? And so since we have a derivative of temperature with respect to time, which is really hard to describe because they're both t's. And so if you're listening to this without looking at the screen, I'm gonna say dt dt, and that seems like it makes no sense, but it's d capital T, d little t, okay? Right, and so this is the derivative of temperature with respect to time. This tells us that this represents any kind of unsteadiness in our equation. Okay. And so what this term represents is any kind of temporal storage or depletion of energy. Okay. Okay. All right. And so you know, I'll tell you right now that we're not going to do much with this term yet. And so, you know, we're going to assume everything is steady state. And when you assume things are steady state, this term goes away. But we will come back to this in a few weeks. Yeah. Oh, question. Yes. So what is this variable here under the in the denominator? Good point. I kind of skipped over that just because you know, we're running a little bit behind. Which is my fault, by the way. Okay. And so this term here is known as the thermal diffusivity. Okay. Okay. And the thermal diffusivity is basically a measure of how quickly a material can respond to changes in temperature, right? And so I don't want to say too much on it now because, you know, we're going to go through it a lot more in a few weeks. And so for now, I just want to focus on the steady state stuff. Yes, it's an alpha. Yeah. So the symbol for thermal diffusivity is an alpha. Yeah. So don't worry about it too much now. You know, we're going to ignore it, you know, for the first few weeks of the class. But once we get to unsteady conduction, then we'll start taking into account. But for now, we can just kind of ignore it. Yeah. Okay. All right. And so that's the heat equation. And so that's what kind of each term represents. You know, a lot of times, you know, we're going to be making assumptions to cancel out some of these terms, you know, but this is kind of the heat equation in its entirety. Okay. All right. Any questions on this? Okay. And again, you know, if you're interested in the derivation of the heat equation, you know, it's you know, basically it's derived by applying conservation of energy to a very small volume, right? And so we call that a differential element. And so if you're interested in that derivation, I think the book does a really nice job of describing it. You know, but I'll kind of leave that to you guys. And instead, you know, I want to do one example before we leave today. Okay. All right. And so now that we've presented what the heat equation is, let's talk about how we actually solve it. Right? Because remember, you know, what we're interested in from the heat equation is temperature, right? And so we ultimately want to solve the heat equation for big T. Okay. Okay. And to get there, you know, we have to do a couple steps here, right? And so the first step we have to do is we have to apply some assumptions, okay? And so, because right now the equation is a partial differential equation, which is, you know, unless you're very advanced with mathematics, is very difficult to solve. And so we're going to apply some assumptions to simplify it. And then after that, we have to actually solve the differential equation that comes out. And so that involves some kind of, you know, ODE solving, which in this case is going to be easy. It's just going to be a simple integral, and then we have to apply boundary conditions on top of that. Okay. All right, and so let's go over that first step first, right? And so let's apply some assumptions. All right, and so you've probably heard about assumptions from your previous classes. Hopefully, if you've had Dr. Weiss before, I know you've talked about assumptions because she talks about it a lot. But applying assumptions is a really important part of doing any kind of engineering analysis, right? Because a lot of times our equations are a little bit too complicated for us to solve by hand, even in the most practical sense, right? And a lot of times you have to apply some assumptions to simplify your life a little bit. And so applying these assumptions and knowing what they do and knowing how to justify them is a really key skill. It's a really central skill in order to perform, engineering at any level, basically. Okay. All right. And so for the heat equation, thankfully the assumptions that we're applying are fairly straightforward. Okay. And so there's two assumptions that we're going to make. Okay. Right. And so the first assumption that we're going to make is what's known as the steady state assumption. Okay. And so the steady state assumption basically assumes that our temperature distribution does not change with time. Okay. And so this tells us basically that any derivative with respect to time is going to be 0. Okay. And so if we have any term that has a derivative with respect to t, little t, then we can just set that equal to 0. And so if we look back at our heat equation, we know that we have this term right here. Okay. And so under the steady state assumption, we can basically just assume that this term is going to go away. Okay. Which is great news for us because, then that simplifies our life quite a bit. Okay. Right. And so this steady state assumption, this is something that we're almost always going to make. And so, this is almost always going to be there. Okay. For the time being. Okay. Okay. So you can always assume this for now. Okay. Later on, when we do unsteady conduction, we'll relax this assumption. Okay, and so we'll bring it back into the fold. But for now, we can just say that we assume this is there. Okay. And so another assumption that we have to make is with regards to the production term. Okay. And so another common assumption that we can make is we assume that there's no production. Okay. And so, with no production, we're basically assuming that there's no conversion of thermal energy occurring within this system. Okay. Right. And so basically that tells us that our production term, which remember was Q dot over K, we can set that equal to 0 as well. Okay. All right. And so under both of those assumptions, we cross out those two terms. We're left with just the diffusion term after that. Right. Okay. And so after those assumptions, we're left with the following differential equation. Okay. Which simply states that the second derivative of temperature with respect to space is equal to 0. Okay. And you'll notice that I changed the partial derivatives here to regular derivatives, right? And so if you remember in the original heat equation, I had partial squared T over partial X squared, that's equal to 0. Okay. But since we've eliminated the time dependence, then we can change the derivative there to regular ones. Okay, and so now we can just do regular integrals on everything. Okay. Any questions on this? Okay. All right, and so that's the first step, right? And so hopefully, this process of applying assumptions and simplifying the equation, hopefully that's familiar to you because that's hopefully something you've done at least in fluid mechanics. Okay. All right, and so after we applied the assumptions and we've simplified our equations, the second step is to actually solve that equation. And in this case, since we have a differential equation, we have to apply boundary conditions as well. Okay. Okay. And so, hopefully you remember a lot from 308 because, we're going to be using a lot of that stuff. Okay. All right. And so I do want to talk about the different types of boundary conditions that you can have. But, we are running a little bit low on time. And so I did want to make sure I go through this example before we go. And so let me go ahead and do this example now because the boundary conditions are fairly simple. And if we have time after that, then we can talk about the other boundary conditions that can occur. Okay. All right, so let's do an example. Okay. All right, and so let's say that we are interested in computing the temperature distribution in a window pane. Okay. Okay. And so on one side of the window pane, we have the outside temperature, which we'll call T infinity. And then on the other side of the window pane, you have your inside temperature, which we'll call Ti. Okay. All right, so let me go ahead and draw the figure for that. Okay. And so here's your window. And so, normally we look at a window from kind of face on like this. Imagine that you're kind of looking at a window from the side. And so you're kind of, you're looking at through the thickness of the window pane. Okay. And so on one side of the window pane, we have the outside world. Okay. And on the other side of the window pane, we have the inside world. Okay. And so on the outside of the window pane, we have the outside temperature, which we'll call T infinity. Okay. And on the inside of the window pane, we have the inside temperature, which is Ti. Okay. And the length of this window pane, we'll say is length L. Okay, such that the x coordinate of the outside, we'll call that 0, and the x coordinate of the inside, we'll call that L. Okay. All right. And so we're interested in computing, what the temperature distribution looks like inside this window pane. Okay. All right. And so before we do that, we have some assumptions. Okay. We always have to list our assumptions. Okay. All right. And so in this, the first assumption we're going to make is that the situation is one-dimensional. And so we're only going to look at the temperature distribution from the left to the right. And so we have a 1D case. Okay. Right. Next, we're going to assume that our situation is steady state. Okay. And then the third assumption we're going to make is that there's no production and no generation. Okay. We'll assume that you don't have a heated window or something like that. And so there's no heater inside your window. Okay. All right. Okay. And then another thing that we can state on here before we actually go to solve is we can state the boundary conditions. Okay. Okay. And so the boundary conditions basically just state, what the temperature looks like at the boundaries of our domain. Okay. And so we're going to need these in order to solve the differential equation, right? And so, I'm hoping that we can talk about boundary conditions in a bit. But basically, in order to get the boundary conditions, you have to look at what's given to you in the problem at the extremities of the domain. Okay. And there are the two extremities of our domain are going to be x is equal to 0 and x is equal to L. Okay. And so we have to define what the temperature looks like at these locations. Okay. All right. And so the temperature at x is equal to 0, which is the outside world, right? We know that the temperature here is equal to T infinity, right? And so that's going to be our first boundary condition. Okay. So T of 0 is equal to T infinity. Okay. And then our second boundary condition, which occurs at x is equal to L. Okay. So we have T as x is equal to L. This is equal to Ti. Okay. And so in this case, we have pretty simple prescribed boundary conditions, and they are, the temperature is prescribed at one end, and the temperature is prescribed at the other end. Okay. All right. And so with this situation, under these assumptions, we're going to take our heat equation and we're going to solve it for the temperature distribution inside this wall. Okay. All right. Any questions on the problem setup? All right. Okay, so let's go ahead and start. Let's just for completeness, let's go ahead and start with our full heat equation. We'll go ahead and cancel out terms due to our assumptions, and then we'll go ahead and solve it. Okay. All right, and so remember our full heat equation is given by partial squared T partial x squared plus Q dot over K is equal to 1 over alpha partial T partial little t. Okay. All right, so let's apply our assumptions. And so remember our first assumption is that we have, well, first of all, it's one dimensional, and that's already kind of implicitly assumed here. The next assumption that we have is that it's steady state, right? And so we can go ahead and cross out that term, right? And so remember, steady state means that any derivative with respect to time is set equal to 0. Okay. And then the other assumption that we have is no production. Right. And so no production means that we can cancel out that term. And so after performing those cancellations, we're left with just d squared t dx squared is equal to 0. Okay. And then a good thing about this is that, yes, this is a differential equation, but it's a fairly simple one. Okay. Okay. And so we have a simple ODE, and we have such a simple one like this, we can solve it by just integrating. Okay. And so we don't have to pull out any of the 308 stuff yet, but later on we're going to see differential equations that are a bit more complicated, and for those ones, you're going to have to use some techniques from 308, so things like integrating factors, things like characteristic equations, and things like that. Okay, but for now we can just simply integrate this and solve. All right, and so let's go ahead and start that process. All right, so if we take the integral of both sides, on the left-hand side, we have just the first derivative of temperature. Okay, and so we have dt dx. Okay, and since we're doing indefinite integrals here, let me go ahead and add a dx here. Okay. Since we're doing indefinite integrals, we take the integral of 0, what we get is some arbitrary constant, so we'll call that C1, right? Right, and so we're going to take the integral again, okay? Okay, and so we take the integral again. On the left-hand side, we're left with t of x, okay? On the right-hand side, we're taking a derivative of a constant. And so the derivative of the integral of a constant is, that constant times x. And so we have C1 times x. Okay. And then once again, since we have, since we're doing an indefinite integral, and so that means we have no bounds on the integral, that means we have to add an arbitrary constant to this as well. Okay. And so I'll call that new arbitrary constant C2. Okay. All right. And so our solution for the temperature here is T of x is equal to C1x plus C2. And so we're not done yet. And so, in order to fully solve this problem, we have to solve for each of those constants, C1 and C2. And the way we do that is through, through the use of boundary conditions. Okay. All right. And so, the next step of this problem is to apply our two boundary conditions, and we're going to solve for C1 and C2. Any questions on this? Okay. All right, so let's go ahead and finish this problem off. All right, and so remember we had our two boundary conditions. And so our first boundary condition was T of 0 is equal to T infinity. Okay. So let's go ahead and plug it in. We're going to plug that into our general solution that we found on the previous page. Okay. And so we plug x is equal to 0. We're going to have C1 times 0 plus C2, right? So all I did was I just plugged in 0 for x from the previous page. Okay. Okay. And so this is equal to T infinity. We're going to get rid of that term because we have C1 times 0, and anything times 0 is going to be 0. Okay. And so this gives us C2 is equal to T infinity. Okay. Right. And so now we're going to apply our other boundary condition, which is T of L is equal to Ti. Okay. And so we go ahead and plug it in. And so we have T of x is equal to L is equal to C1 times L plus C2. But we've already determined C2 from the previous equation. And so we know C2 is equal to T infinity. Okay. And on the right-hand side, we're going to have Ti. Okay. And so we, if we solve for this, then we get C1 is equal to Ti minus T infinity all divided by L. Okay. Right. And so now that we have C1 and C2, we can go ahead and plug these into our temperature equation. And what we get is T of x is equal to C1 times x. And so we have C1, which is Ti minus T infinity all divided by L times x plus C2, which is T infinity. Okay. Right. And so this equation right here expresses, what the temperature distribution looks like inside that window pane. Okay. All right, and so since we have just a linear function here, this tells us that the temperature distribution in the window pane is linear. Okay. Okay. And so if I were to draw this on the window pane, I'll come back to that in a second. Okay. So this tells us that there's just going to be a linear difference in between T infinity and Ti. Okay. So we have just a simple linear change in temperature, just like that. Okay. Oops. All right. Any final questions on this before we wrap it up for the week? All right. Okay. So that's all we got time for this week. And so on Monday when we pick this up, I'll go ahead and talk about the different types of boundary conditions that we can have. Because so far we've just seen just the one, which is just prescribed temperature, but there's a couple other more that you should know, before we move forward. And then from there, we're going to talk about the idea of a thermal resistance. Okay. And so if you hated circuits before, well, too bad, you're going to see it again, right? And so, we're going to see how we can apply circuit methodology to heat transfer. Okay. All right. So thank you everyone for tuning in today. That was kind of the end of our first week. Next week, we're still going to be virtual. So remember to meet here on Zoom. Okay. So have a great weekend, everyone. And I will see you on Monday.
Thank you, Professor. Have a good weekend.
Thanks, you too.
Professor.
Yeah,
Thank you,
thanks,
Dr.
Professor.
Thanks, guys.
Thanks, Prof. How likely is it that we're going to stay from that we're going to go back to class? Like,
Honestly, I have no idea. I mean, right now the current plan is to go back after these first 2 weeks. But the COVID situation is changing kind of day by day, and so they might make another announcement that they're going to extend this virtual instruction. So honestly, I have no idea, and I'm not part of that decision making. I just go along with what they say.
All right then. Thanks, Prof.
Thanks. Can I send the ISBN of the book? Yes. Yes, I can. But Dustin, you had a question as well. Let me go ahead and stop the recording for now.